So hello everyone, I'm Antoine Espagnet. I'm a PhD student working in Toulouse at IRAP. I'm working in the Chemtrip ERC project with Audrey Coutens, and I'm working on modeling the chemical impacts of luminosity outbursts in protostellar envelopes. So to start, spectral surveys in the radio, submillimeter, and millimeter allows us to probe the molecular composition of star-forming regions. So far, observational studies seems to indicate that the chemical content may differ between protostars, and thus we use physical-chemical models to understand the origins of these differences. So in this study, as I'm interested in the envelope, I will mainly focus in the class 0 and class 1 stages of the low-mass star formation process, because this is where we have an envelope around the protostar. So some of those protostars undergo episodic accretion, which consist in long periods of low accretion rate, which are called the quiescent phases, with short periods with high accretion rate, which are called the outburst phase. And those episodic accretion from the disk to the protostar caused luminosity outbursts of the protostar. And here you have a representation of the transition between the quiescent phase to the outburst phase, where you can see the magnetospheric accretion from the disk onto the protostar. So the question I want to answer is, what is the impact of those luminosity outbursts on the chemical composition of solar type protostellar envelopes? So from the warm inner regions, so close to the protostar, to the cold outer regions. So if we look at what is inside the envelope, we see gas and dust. So if we are far away the protostar, the temperature is low and the molecules are frozen on the surface of grains. And if we are close to the protostar, the temperature is high enough to melt the ices, and molecules will be in the gas phase. And the interface between the two is called the snow line here. And for complex organic molecules that are carbon-bearing species of at least 6 atoms, this snow line is located at about 100 AU for low-mass protostars. So we are going to take this sketch of protostellar systems, our quiescent phase, so without any luminosity outburst for now. And when the outburst is going to occur, the luminosity of the protostar will increase a lot, and it will heat up the envelope, pushing away the snow lines from the protostar at larger radii in the envelope. And this will release molecules in the gas phase, which is called thermal desorption. And what we want to probe is if this release of molecules into the gas phase can have an impact on the chemistry at the long term. So to do that, I used models, and I did the simulation of material inflow in the envelope. So I did 1D model with particles that are falling in the protostellar envelope with different trajectories. And in this model, particles experience the outburst at different points in their trajectories. So first, I have a fiducial model without any luminosity outburst. This model is composed with a physical model and a chemical model. For the physical model, I use IRAP, which is a code which is developed by Pierre Marchand in Toulouse. It's a semi-analytical model, which includes dynamics. And for the chemical model, I use Nautilus, which is developed here in Bordeaux. And thus, at the end, I retrieve chemical abundances. So here you have a picture of what I obtain with each model. So the physical model provides the time evolution of physical parameters for particles, so the temperature and the density according to time, but you also have the position, the visual extension, and so on. And using this as input for the chemical model, we can retrieve the chemical abundances for every molecule we have in the network, both in the gas and in the ice phase, according to time. And thus, then I did the same with the outburst impacted model. So just before putting the physical parameters in Nautilus, I implemented an outburst and then used those modified physical parameters with Nautilus to retrieve chemical abundances and compare chemical abundances both in the case impacted by the outburst and not. So to implement the outburst, I took the quiescent phase calculated by IRAP. So this is temperature according to time for a particle. Then I put an outburst, which lasts 100 years in my model. And during the outburst, the luminosity of the protostar will be increased by a factor 100 and only impacts the temperature through the Stefan-Boltzmann equation. And then we go back to the quiescent phase calculated by IRAP. So doing this using several particles, we can retrieve radial profile of abundances. So in this example, you have the gas phase methanol here, according to the radius in the protostellar envelope. And here on the top, you have the corresponding quiescent temperatures at different radius in the protostar. So in black, you have the radial profile in the quiescent case, so without any luminosity outburst, and in colors, it's for the outburst impacted models at different time after the beginning of the outburst. So in purple, it will be 10 years after the beginning of the outburst. In blue, it will be 100 years and so on. So here we have 2 times that are during the outburst, as the outburst is lasting 100 years, and 5 that are post-outburst times. And this is for an outburst which is triggered 100,000 years after the beginning, the birth of the protostar. And as our model includes dynamics, the temperature profiles, density profile are evolving during the life of the protostar, and we don't want to be biased by this choice. So we made this time varies from 1,000 years to 100,000 years. And this produces the spreads you have in the gray vertical bands that are the temperatures, and also in the abundance profiles. And here, for the example of methanol, you can see that the gas phase is expanded. So the region where the gas phase is high will be larger than in the quiescent state. And I will call that chemical expansion afterwards. And of course, we can do this for every chemical species of the network. So first, as expected, we obtained a chemical expansion for a lot of molecules, about 300 of them. And here you have examples for complex organic molecules with chemical thermal disruption temperature of about 100 K. So for all of those molecules, we observe a chemical expansion, and then the gas phase abundance slowly returns to the quiescent state. We also observe a similar behavior for smaller and lighter molecules, as CO or methane, for example, but further away in the envelope with thermal disruption temperature that are lower. We can also determine whether this chemical expansion is due to thermal disruption or not. So to do that, we can look at the different phases of the molecules. So here you have the gas phase, what I was showing just before. You have also the ice phase and the total abundance for methanol and methanoic acid here. So for methanol, you can see that the total abundance is not changing. So we can determine that we have a transition from the ice phase to the gas phase and only this, which is not the case for methanoic acid, where we can see that the chemical expansion we observe here is due to production of this molecule And here we can also observe destruction in the ices during the outburst. We also observed an increase or decrease of abundances in the warm northern region a long time after the outburst occurred, as you can see here for glycoaldehyde, for example. So this is a gas phase abundance profile of glycoaldehyde. So if you want to see clearer, here, this is the profile 10,000 years after the outburst occurred. And we observe here in the inner region a decrease in the gas phase abundance. This is due to the fact that during the outburst, the reservoir of molecules used to form glycoaldehyde in ices in the outer part of the envelope will be destroyed, leading to a less efficient formation of glycoaldehyde. Okay, a less efficient formation of glycoaldehyde in the outer part of the envelope. And this discrepancy will be kept in the particle during their travel in the envelope. And once they are going to reach the inner part, where the temperature is high enough to dissolve glycoaldehyde, we will see this discrepancy in the gas phase here. And this is the case for about 60 molecules in the network we have. We also observe for a lower number of molecules, a bump here happening during the outburst, and which lasts for about 1,000 years. A bump here in the 30 to 50K region. This is due to the fact that there is no ICs of those molecules in the inner part, so no desorption is possible here. And there is a lot of those ICs in the outer part here. So during the outburst, the desorption temperature will be reached in this region, leading to only a located desorption region. So to summarize, I'm doing modeling of the chemistry of protostellar envelopes using IRAP and Nautilus. And more precisely, I'm studying the impact of luminosity outbursts on the chemistry. We found, as expected, a chemical expansion for the majority of the molecules, about 300, and also an increase and a decrease in gas phase abundance. So in the warm inner region, where the temperature is higher than 100K, at long term for about 60 molecules, and in a colder region of about 30 to 50K region at shorter term for about 10 molecules. Thank you.